Welcome to Network Troubleshooting Part 2. On Part 1, we talked about network documentation, troubleshooting process, and troubleshooting tools. On this video lecture, which is the Part 2, we will be talking about symptoms and causes of network problems, troubleshooting IP connectivity. Okay. So let's talk about the symptoms and causes of network problems. So let's start with the physical layer troubleshooting. So the figure here summarizes the symptoms and causes of a physical layer network problems. Now that you have your documentation, some knowledge of troubleshooting methods, and the software and hardware tools to use to diagnose problems, you are ready to start troubleshooting now. So this topic covers the most common issues that you will find when troubleshooting a network. So as a system administrator or network administrator, this will help you troubleshoot a problem. So issues on the network often present as performance problems. Performance problems mean that there is a difference between the expected behavior and the observed behavior, and the system is not functioning as could be reasonably expected. So failures and suboptimal conditions at the physical layer not only inconvenience users but can impact the productivity of the entire company. So networks that experience these kinds of conditions usually shut down. Because the upper layers of the OSI model depend on the physical layer to function, a network administrator or systems administrator must have the ability to effectively isolate and correct problems at this layer. Okay, so the symptoms includes performance lower than the baseline, loss of connectivity, network bottlenecks or congestion, high CPU utilization rates, and console error messages. So possible causes includes power-related problems, hardware faults, cabling faults, attenuation, noise, interface configuration errors, exceeding design limits, and CPU overload. Okay? Now, let's talk about it in detail. So starting with the performance lower than the baseline. So the description would be it requires previous baselines for comparison. So the most common reasons include overloaded or underpowered servers, so unsuitable switch or router configurations, traffic congestions or congestions on a low capacity link, and chronic frame loss. Okay, so loss of connectivity, it could be loss of connectivity could be due to a failed or disconnected cable. So it can be verified using a simple ping test. So you can go ahead on the client, okay, and run the ping test. Okay, you can also use this ping command on any of the network devices. So intermittent connectivity loss can indicate a loose or oxidized connection. So you have to check your cable or the connectivity. Okay, so the third one is network bottlenecks or congestion. So if a route fails, routing protocols could redirect traffic to suboptimal routes. So this can result in congestion or bottlenecks in parts of the network. Okay. Next is high CPU utilization rates. So high CPU utilization rates indicates that a device is operating at or exceeding its device limits or design limits. So if not adjusted quickly, CPU overloading can cause device to shut down or fail. Okay. So, and the last one is console error messages. So error messages reported on the device console could indicate a physical layer problem. So console messages could be logged to a central syslog server. All right. Okay, so let's talk about the problem cause. Okay, so this table lists issues that commonly cause network problems at the physical layer. So this includes the power related problem. Okay, so when you say power related, this is the most fundamental reason of network failure. Okay, so you need to check the operation of the fans and ensure that the chassis intake and exhaust vents are clear If other nearby units have also powered down, suspect a power failure at the main power supply. So the next one is hardware faults. Okay, so faulty network interface cards can cause network transmission errors due to late collisions, short frames, and jabber. Jabber is often defined as the condition in which the network device continually transmits random, meaningless data onto the network. Others likely causes of jabber are faulty or corrupt NIC driver files, bad cabling, or grounding problems. Next is cabling faults. So many problems can be corrected by simply resetting cables that have become partially disconnected. So when performing a physical inspection, look for damaged cables, improper cable types, okay, and poorly crimped RJ45 connectors. So suspect cables should be tested or exchanged with a known good or functioning cable. Next is attenuation. So attenuation can be caused if a cable length exceeds the design limit for the media, and when there is a poor connection resulting from loose cable or dirty or oxidized contacts. So if attenuation is severe, the receiving device cannot always successfully distinguish one bit in the data stream from another bit. Okay? Noise. So local electromagnetic interference, or EMI, is commonly known as noise. Noise can be generated by many sources such as FM radio stations, police radio, building security, and avionics for automated landing. So crosstalk, or noise influenced by other cables in the same pathway or adjacent cables. Also, nearby electric cables, devices with large electric motors, or anything that includes transmitter more powerful than a cell phone. Okay? Also is the interference or interface configuration errors. So many things can be misconfigured on an interface to cause it to go down, such as incorrect clock rate, incorrect clock source, okay? Interface not being turned on. That's common. So this causes a loss of connectivity with attached network segments. Okay? How about exceeding design limits? So a component may be operating suboptimally at the physical layer because it is being utilized beyond specifications or configured capacity. So when troubleshooting this type of problem, it becomes evident that resources for the device are operating or at near maximum capacity, and there is an increase in the number of interface errors. Last one is CPU overload. So symptoms include processes with high CPU utilization percentages, input queue drops, slow performance, SNMP timeouts, no remote access, or services such as DHCP, Telnet, and Ping are slow or fail to respond. So on a switch, the following could occur: spanning tree reconvergence, okay, Ethernet links bounce, UDLD flopping, IP SLAs failures. So for routers, there could be no routing tables or no routing updates, route flopping, or HSRP flopping. So one of the causes of CPU overload in a router or switch is high traffic. So if one or more interfaces are regularly overloaded with traffic, consider redesigning the traffic flow in the network or upgrading the software or hardware. Okay? Alright, so let's move on to the data link layer troubleshooting. So the figure summarizes the symptoms and causes of the data link layer network problems. Okay, so troubleshooting layer 2 problems can be a challenging process. The configuration and operation of these protocols are critical to creating a functional, well-tuned network. So layer 2 problems cause specific symptoms that, when recognized, will help identify the problem quickly. Okay, so the symptoms on the data link layer includes no functionality or connectivity at the network layer or above, network operating below the baseline, okay, or below performance levels, excessive broadcasts, and console messages. So possible causes includes encapsulation errors, address mapping errors, framing errors, and STP failure or loops. Okay? Network is operating below the baseline performance level. Now, first, the frames take a suboptimal path to their destination, but do arrive, causing the network to experience unexpected high bandwidth usage on links. Second, some frames are dropped as identified through error counter statistics and console error messages that appear on the switch or router. And an extended or continuous ping can help reveal if frames are being dropped. Okay? Next, console messages. Okay, so for console messages, a router recognizes that a layer 2 problem has occurred and sends alert messages to the console. So typically, a router does this when it detects a problem when interpreting incoming frames, encapsulation or framing problems, or when keep alives are expected but do not arrive. So the most common console message that indicates layer 2 problem is the protocol down message. Okay? Next. So encapsulation errors. An encapsulation error occurs because the bits placed in a field by the sender are not what the receiver expects to see. This condition occurs when the encapsulation at one end of the one link is configured differently from the encapsulation used on the other end. Address mapping errors. So in topologies such as point-to-multipoint or broadcast Ethernet, it is essential that an appropriate layer to destination address be given to the frame. So this ensures its arrival at the correct destination. So to achieve this, the network device must match destination layer 3 address with the correct layer 2 address using either static or dynamic maps. In a dynamic environment, the mapping of layer 2 and layer 3 information can fail because devices may have been specifically configured not to respond to ARP requests. So the layer 2 or layer 3 information that is cached may have physically changed, or invalid ARP replies are received because of misconfiguration or a security attack. Okay? How about framing errors? So frames usually work in groups of 8-bit bytes. So a framing error occurs when a frame does not end on an 8-bit byte boundary. So when this happens, the receiver may have problems determining where one frame ends and another frame starts. So too many invalid frames may prevent valid keep alives from being exchanged. So framing errors can be caused by noisy serial line, and improperly designed cables, too long or not properly shielded, faulty network interface card, duplex mismatches, or an incorrectly configured channel service unit or CSU line like clock. Okay? Okay, so the last one is STP failures, or the spanning tree protocol failures or loops. So the purpose of spanning tree protocol is to resolve a redundant physical topology into a tree-like topology by blocking redundant ports. So most STP problems are related to forwarding loops that occur when no ports in a redundant topology are blocked and traffic is forwarded in circles indefinitely. So this causes excessive flooding because of a high rate of STP topology changes. A topology change should be a rare event in a well-configured network. So when a link between two switches goes up or down, there is eventually a topology change when the STP state of the port is changing to or from forwarding. However, when a port is flapping, okay, oscillating between up and down states, okay, so this causes repetitive topology changes and flooding, or slow STP convergence or reconvergence. So this can be caused by mismatched between a real and documented topology, a configuration error such as inconsistent configuration of STP timers, an overloaded switch CPU during convergence, or a software defect. Okay? Okay, so next would be the network layer troubleshooting. So the figure summarizes the symptoms and causes of the network layer problems. Okay, so symptoms like network failure, suboptimal network performance, okay, causes like general network issues, connectivity issues, routing tables, neighbor issues, and topology database. So network layer problems include any problem that involves a layer 3 protocol, such as IPv4, IPv6, EIGRP, OSPF, or any routing protocols. Okay, now the table lists common symptoms of network layer problems. Okay, so like network failure and suboptimal network performance. Now for the network failure is when the network is nearly or completely non-functional, affecting all users and applications on the network. So these failures are usually noticed quickly by users and network administrators or systems administrators, and are obviously critical to the productivity of the organization or of the company. Suboptimal performance, okay? So network optimization problems usually involve a subset of users, applications, destinations, or a type of traffic. So optimization issues can be difficult to detect and even harder to isolate and diagnose. So this is because they usually involve multiple layers or even a single host computer. So determining that the problem is a network layer problem can take time. Okay, so in most networks, static routes are used in combinations with dynamic routing protocols. Improper configurations of static routes can lead to less than optimal routing. So in some cases, improperly configured static routes can create routing loops, which make parts of the network unreachable. Troubleshooting dynamic routing protocols requires a thorough understanding of how the specific routing protocols functions. So some problems are common to all routing protocols, while others are particular to an individual routing protocol. So there is no single template for solving a layer 3 problems. Okay, so routing problems are solved with a methodological process using a series of commands to isolate and diagnose problems. Okay. Also, now this table lists common symptoms of network or layer problems. Okay, so let's talk about the general network issues. Okay, so often a change in the topology, such as downlink, may have effects on other areas of the network that might not be obvious at the time. Okay, so this include the installation of new routes, static or dynamic, or removal of other routes. Determine whether anything in the network has recently changed and if there is anyone currently working on the network infrastructure. Connectivity issues. So check for any equipment and connectivity problems, including power problems, such as outages and environmental problems, for example, overheating. Also, check for layer 1 problems, such as cabling problems, bad ports, and ISP problems. You could also have problem on routing table. So check the routing table for anything unexpected, such as missing routes or unexpected routes. So you can use the debug commands to view routing updates and routing table maintenance. Okay, you also need to check neighbor issues, maybe. So if the routing protocol establishes an adjacency with a neighbor, check to see if there are many or any problems with the routers forming neighbor adjacencies. Also with the switch. Okay, and maybe it's on topology database. So if the routing protocol uses a topology table or database, check the table for any unexpected, such as missing entries or unexpected entries. Next, transport layer troubleshooting. So this merely focuses on the access control lists. Okay, so network problems can arise from transport layer problems on the router, particularly at the edge of the network where traffic is examined and modified. So for instance, both access control lists or ACL and network address translations or NAT operate at the network layer and may involve operations at the transport layer, as shown here in the diagram. Okay, so symptoms like connectivity issues, okay, so access issues, this could cause or caused by ACL configurations or the network address translation configurations. Okay, so the most common issues with ACLs are caused by improper configurations, as shown here. Okay, so common ACL misconfigurations like selection of traffic flow, order of ACL entries, implicit deny, okay, any, address and IPv4 wildcard masks are improperly used, selection of transport layer protocols, okay, so something like, is it a UDP or really a TCP, okay, so source and destination ports, sometimes the use of the established keyword, and uncommon protocols. Okay, now let's deal with it individually. So let's start with the selection of a traffic flow. So traffic is defined by both the router interface through which the traffic is traveling and the direction in which the traffic is traveling. So an ACL must be applied to the correct interface, and the correct traffic direction must be selected to function properly. Okay, so next would be the order of access control entries. So the entries in an ACL could be from specific to general. Okay, this is a common error. Okay, so when you do your ACL, make sure you listed it from specific down to general. So although an ACL may have an entry to specifically permit a type of traffic flow, packets never match the entry if they are being denied or, okay, not permitted, okay, denied by another entry earlier in the list. Okay, so if the router is running both ACL and NAT, the order in which each of these technologies is applied to the traffic flow is important. So inbound traffic is processed by the inbound ACL before being processed by the outside to inside NAT. So outside traffic is processed by the outbound ACL after being processed by inside to outside NAT. Okay, so you have to carefully test and check your configuration. Okay, next is implicit deny any. So when high security is not required on the ACL, this implicit access control element can be cause of an ACL misconfiguration. Okay, so also the address and IPv4 wildcard masks. This is also a common error. So complex IPv4 wildcard masks provide significant improvements in efficiency but are more subject to configuration errors. So an example of a complex wildcard mask is using the IPv4 address 10.0.32.0 and wildcard masks 0.0.32.15. Okay, so to select the first 15 hosts addresses in either the 10.0.0.0 network or the 10.0.32.0 network. Okay, so you have to carefully analyze, okay, so the use of the wildcard mask. Wildcard mask is the opposite of subnet mask. Remember that. Okay, so next is the selection of transport layer protocol. So when configuring an ACL, it is important that only the correct transport layer protocols are specified. Okay, so many network administrators and systems administrators, when unsure whether a type of traffic flow uses a TCP port or a UDP port, configure both. Okay, so specifying both opens a hole through the firewall, so possibly giving intruders an avenue into the network. So it also introduces an extra element into the ACL. So the ACL takes longer to process, introducing more latency into network communications. Okay, so next is source and destination ports. So properly controlling the traffic between two hosts requires symmetric access control elements for inbound and outbound ACLs. So address and port information for traffic generated by replying hosts is the mirror image of an address, and port information for traffic generated by initiating hosts. Use of the established keyword could also be a misconfiguration. Okay, so the established keyword increases the security provided by the access control list. However, if the keyword is applied incorrectly, unexpected results may occur. Okay, also, you've got the uncommon protocols. Okay, so misconfigured ACLs often cause problems for protocols other than TCP and UDP. So uncommon protocols that are gaining popularity are VPN, or the Virtual Private Network, and encryption protocols. Okay, so the log keyword is a useful command for viewing access control list operations on the ACL entries. So this keyword instructs the router to place an entry in the system log whenever that entry condition is matched. So the logged event includes details of the packet that matched the ACL element. So the log keyword is specifically or especially useful for troubleshooting and provides information on intrusion attempts being blocked by the access control list. Okay? Next, how about transport layer troubleshooting, not for IPv4? Okay, so common interoperability areas includes BOOTP, DHCP, DNS, WINS, SNMP, and tunneling and encryption protocols. Okay, so there are several problems with NAT, such as not interacting with services like DHCP and tunneling. So this can include misconfigured NAT inside or NAT outside. So mostly, okay, students tend to forget, okay, to include IPNAT inside and IPNAT outside, or the access lists. So other issues include interoperability with other network technologies, especially those that can contain or derive information from host network addressing in the packet. Okay? For BOOTP and DHCP, so both protocol manage the automatic assignment of IP addresses to the clients. So recall that first packet that new client sends is a DHCP request broadcast IPv4 packet. So the DHCP request packet has a source IPv4 address of 0.0.0.0. Okay, so because NAT requires both valid destination and source IP address, the BOOTP and DHCP can have difficulty operating over a router running either static or dynamic NAT. So configuring the IPv4 helper feature can help solve this problem. Okay, how about on DNS? Okay, symptoms on DNS. So because a router running dynamic NAT is changing the relationship between inside and outside addresses regularly as table entries expire and are recreated, a DNS server outside the NAT router does not have an accurate representation of the network inside the router. So configuring the IPv4 helper feature can also solve the problem. Okay? Next is the Simple Network Management Protocol, or SNMP. So like DNS packets, NAT is unable to alter the addressing information stored in the data payload of the packet. So because of this, an SNMP management station on one side of a NAT router may not be able to contact the SNMP agents on the other side of the NAT router. So configuring the IPv4 helper feature can help solve this problem also. Okay? And the last one is tunneling and encryption protocols. So encryption and tunneling protocols often require the traffic be sourced from the specific UDP or TCP port, or use a protocol at the transport layer that cannot be processed by NAT. For example, IPsec tunneling protocols and generic routing encapsulation protocols used by VPN implementations cannot be processed by network address translator. Okay? Now let's move on to the application layer troubleshooting. Okay, so the figure shows the most widely known and implemented TCP/IP application layer protocols. So the application layer troubleshooting, most of the application layer protocols provide user services. Application layer protocols are typically used for network management, file transfer, distributed file services, terminal emulation, and email. So new user services are often added, such as VPNs and the VoIP. Okay, so here are some of the well-known application layer protocols used. Now the table provides a short description of these application layer protocols, like SSH or Telnet, which is used to allow the users to remotely connect to a device. You also have the HTTP. It supports the exchanging of text, graphic, images, sound, video, and other multimedia files on the web. Okay? FTP performs interactive file transfers between hosts. You also have the TFTP, which performs basic interactive file transfers, typically between hosts and networking devices like routers and switches. SMTP supports basic message delivery services. You've got POP or POP, connects to mail servers and download emails. SNMP, it collects management information from network devices. DNS maps IP address to the names assigned to the network devices. And you also have the NFS, or the network file system, enables computers to mount and use drives on remote hosts. Okay? Now, originally, these network file systems, or NFS, is developed by Sun Microsystems. It combines with two other application layer protocols, External Data Representation or XDR, and the Remote Procedure Calls or RPC to allow transparent access to remote network resources. Okay, now the types of symptoms and causes depend upon the actual application itself. So application layer problems prevent services from being provided to application programs. A problem at the application layer can result in unreachable or unusable resources when the physical, data link, network, and transport layers are functional. It is possible to have full network connectivity, but the application simply cannot provide data. So another type of problem at the application layer occurs when the physical layer, data link, network, and transport layers are functional, but the data transfer and requests for network services from a single network service or application do not meet the normal expectation of a user. So a problem at the application layer may cause users to complain that the network or an application that they are working with is sluggish or slower than the usual when transferring data or requesting network services. Okay, so let's talk about troubleshooting IP connectivity now. So components of troubleshooting and end-to-end connectivity. So this topic presents a single topology and the tools to diagnose, and in some cases, solve an end-to-end connectivity problem. So diagnosing and solving problems is an essential skill for systems administrators and network administrators. There is no single recipe for troubleshooting, and a problem can be diagnosed in many ways. However, by employing a structured approach to the troubleshooting process, an administrator can reduce the time it takes to diagnose and solve the problems. Now, assuming that we have a problem on end-to-end connectivity, so you can use the bottom-up approach when there is no end-to-end connectivity, and these steps are as follows. Okay, So first, you need to check physical connectivity at the point where network communication stops. Check for duplex mismatches. Check data link and network layer addressing on the local network. Verify the default gateway is correct. Ensure that devices are determining the correct path from the source to destination. Verify the transport layer is functioning properly. Verify that there are no ACLs blocking the traffic, and ensure that DNS settings are correct. Okay, so throughout this topic, the following scenario is used. The client host PC1 is unable to access applications. Okay, so this is your PC1, unable to access applications on the server 1. Okay, or server 2. So the figure shows the topology on this network. PC1 uses Slack with EUI64 to create its IPv6 global unicast address. The EUI64 creates the interface ID using the MAC address, inserting FFFE in the middle, and flipping the 7th bit. So when there is no end-to-end connectivity and the administrator chooses to troubleshoot with a bottom-up approach, so the following are common steps the administrator can take. So we have mentioned it earlier. Check the physical connectivity, check for duplex mismatches, okay? So check for data link and network layer addressing on the local network. So this includes IPv4 ARP tables, IPv6 neighbor tables, MAC address tables, and VLAN assignments. Okay? On step 4 presented before this slide, you have to verify the default gateway is correct. Ensure that devices are determining the correct path from the source to destination. So manipulate the routing information if necessary. So step 6 is verify the transport layer is functioning properly. So what you can do is Telnet can also be used to test transport layer connections from the command line. Okay, so verify that there is no ACLs blocking the traffic, and we have to ensure that DNS settings are correct. So there should be a DNS server that is accessible. So the outcome of this process is operational end-to-end connectivity. If all other steps have been performed without any resolution, the network administrator or the systems administrator may either want to repeat the previous steps or escalate the problem to a senior administrator. Okay? Okay, so let's dig into the details of those steps presented. So let's start with verifying the physical layer. Okay? So all network devices are specialized computer systems. At a minimum, these devices consist of CPU, RAM, and storage space, allowing the device to boot and run the operating systems and interfaces. So this allows for the reception and transmission of network traffic. So when a network administrator or systems administrator determines that a problem exists on a given device and that problem might be hardware related, it is worthwhile to verify the operation of these generic components. So the most commonly used Cisco IOS commands for this purpose are show processes CPU, or show memory, or show interfaces on some brands or some platform. So they might have their own commands to do this. So this video topic discusses the show interface command. Okay? And when troubleshooting the performance related issues and hardware is suspected to be at fault, the show interface command can be used to verify the interfaces through which the process or the traffic passes. Okay, so this includes the point of interests here. Okay, so something like interface status. Okay, so if it is up or down. Okay, so you could also have the input queue drops. Okay, the input queue drops and the related ignored and throttle counters signify that at some point more traffic was delivered to the router than it could process. So this does not necessarily indicate a problem. That could be a normal traffic during peak periods. However, it could be an indication that the CPU cannot process packets in time. So if this number is consistently high, it is worth trying to spot at which moments these counters are increasing and how this relates to the CPU usage. Okay? You also have the output queue drops. The output queue drops indicates that packets were dropped due to congestion on the interface. Seeing output drops is normal for any given point where the aggregate input traffic is higher than the output traffic. So during peak periods, okay, so packets are dropped in traffic is delivered to the interface faster than it can be sent out. However, even if this is considered normal behavior, it leads to packet drops and queuing delays. So applications that are sensitive to those, such as VoIP, might suffer from performance issues. Consistently, seeing output queue drops can be an indicator that you need to implement an advanced queuing mechanism to implement or modify the quality of service. You also have the input errors. So input errors indicate errors that are experienced during the reception of the frame, such as the CRC errors or the cyclical redundancy check errors. So high numbers of CRC errors could indicate cabling problems, interface hardware problems, or in an Ethernet-based network, duplex mismatches. Okay? Or our interest might be on the output errors. So output errors indicate errors such as collisions. During the transmission of frame in most Ethernet-based networks today, full duplex transmission is the norm, and half duplex transmission is the exception. So in full duplex transmission, operation collisions cannot occur. So therefore, collisions, especially late collisions, often indicate duplex mismatches. Okay? So you can verify, okay, these interests in the outputs, okay? So on this diagram here, by just running show interfaces gigabit 000, for instance, okay? You can see this, the interface status there, which is up and up. Okay, so that's a good indication. That means our port G000 is up and running. Okay, so the input queue, the output queue, you've got the input errors and the output errors are also indicated. So it can be seen on the show interface gigabit Ethernet 0/0/0. So this is a good command to verify the physical layer problem. Okay? Next. So step 2 is you need to check for duplex mismatches. So another common for interface error is a mismatched duplex mode between two ends of an Ethernet link. So in many Ethernet-based networks, point-to-point connections are now the norm, and the use of hubs and the associated hub duplex operation is becoming less common. So this means that most Ethernet links today operate in full duplex mode. And while collisions were normal for an Ethernet link, collisions today often indicate that duplex negotiation has failed, or the link is not operating in the correct duplex mode. So the IEEE 802.3ab Gigabit Ethernet standard mandates the use of auto negotiation for speed and duplex. So in addition, although it is not strictly mandatory, practically all fast Ethernet NICs are also using auto negotiation by default. So the use of auto negotiation for speed and duplex is the current recommended practice. Okay, so this is basically done mostly on the switches connected to another switch or switch to the workstation. However, if full duplex negotiation fails for some reason, it might be necessary to set the speed and duplex manually on both ends. So typically, this would mean setting the duplex mode to full duplex or both ends of the connection. So if this does not work, running half duplex on both ends is preferred over a duplex mismatches. So duplex configuration guidelines includes the following. auto negotiation, and duplex is recommended. So if auto negotiation fails, manually set the speed and duplex on interconnecting ends. So point-to-point Ethernet links should always run in full duplex mode. Okay? So half duplex is uncommon and typically encountered only when you are using the legacy hub. Okay? And nowadays, less are using hubs on their network. Okay? Now, this is an example of duplex mismatch here. So we have here switch 1 and switch 2. They are connected with each other. Okay? So if you will observe here, the status is both up. So you have passed the first step. Okay? So which is verify the physical layer connectivity. But if you will observe in here, switch 1 is running at full duplex, while switch 2 is running at half duplex. So this is what you call duplex mismatches. Okay? Next, step number 3. Verify addressing on the local network. Okay? So when troubleshooting an end-to-end connectivity, it is useful to verify mappings between destination IP address and the layer 2 Ethernet address on individual segments. In IPv4, this functionality is provided by ARP. So in IPv6, the ARP functionality is replaced by the neighbor discovery process and ICMPv6. So the neighbor table catches IPv6 addresses and their resolved Ethernet physical MAC addresses. Okay, so Windows IPv4 ARP table, you can use the command ARP. Okay, so the ARP Windows command displays and modifies entries in the ARP cache that are used to store IPv4 addresses and the result Ethernet physical MAC address. So as shown in the output here, okay, so the ARP Windows command lists all devices that are currently in the ARP cache. Okay, so the information that is displayed for each device includes IPv4 addresses, physical MAC address, and the type of addressing, would it be static or dynamic. So the cache can be cleared by using the ARP-D Windows command, okay, if the network administrator or the system's administrators want to repopulate the cache with an updated information. So note that the ARP commands in Linux and Mac OS X have similar syntax. Okay? Next, troubleshoot VLAN assignment. Okay, so another issue to consider when troubleshooting end-to-end connectivity is the VLAN assignment. In the switch network, each port in a switch belongs to a VLAN. So each VLAN is considered a separate logical network. And packets destined for stations that do not belong to the VLAN must be forwarded to a device that supports routing, like router or layer 3 device. So if a host in one VLAN sends a broadcast Ethernet frame such as an ARP request, all hosts on the same VLAN receive the frame. Hosts in other VLANs do not, of course. So even if two hosts are in the same IP network, they will not be able to communicate if they are connected to ports assigned to two separate VLANs. So additionally, if the VLAN to which the port belongs to is deleted, the port becomes inactive. So all hosts attached to ports belonging to the VLAN that was deleted are unable to communicate with the rest of the network. So commands such as show VLANs can be used to validate VLAN assignments on a switch. Okay, so assume for example that in an effort to improve the wire management in the wiring closet, your company has reorganized the cables connecting to switch 1. So almost immediately afterward, users started calling the support desk, stating that they could no longer reach devices outside their own network. Okay, so you can also check the switch MAC address table. So there were no configuration changes on the router. So switch 1 is focused on troubleshooting, or is the focus of troubleshooting here. Okay, so the MAC address table for switch 1, as shown in the command output, shows that the MAC address of R1, okay, is different from the rest of the 10.1.10.0/24. Okay, that includes or including PC1. Next is you have to have the correct VLAN assignment. Okay, so during the recabling, the patch cable for R1 was moved from FA04 on VLAN 10. Okay, so take a look at the diagram, to FA01 on VLAN 1. So after the system's administrator configured the FA01 port of switch 1 to be on VLAN 10, as shown in the command line, the problem was resolved. So the MAC address table now shows VLAN 10 for MAC address R1 on port FA01. So it's in here. Okay? So you could have simply show VLAN and check if the workstations or both end nodes are located on the same VLAN. So if not, you should have a router between these two devices. Okay, so step 4 is verifying the default gateway. Okay, so if there is no detailed route on the router, or if the host is configured with the wrong default gateway, then communication between two endpoints in different networks does not work. Okay, so the figure illustrates how PC1 uses R1 as its default gateway. So similarly, R1 uses R2 as its default gateway or gateway of last resort. So if a host needs to access resources beyond the local network, the default gateway must be configured. So the default gateway is the first router on the path to destination beyond the local network. Okay? So in this example, R1 has the correct default gateway. Okay? So if this R1 here, okay, if this R1 here has the correct default gateway, which is the IPv4 address of R2, okay, then these two should be able to communicate with each other. However, PC1 has the wrong default gateway here. Okay, so my default gateway is R1. So PC1 should have a default gateway of 10.1.10.1. Okay, so PC1 is directly connected to G000 of R1, which has the IP address 10.1.10.1. Okay, so this must be configured manually if the IPv4 addressing information was manually configured on PC1. So if the IPv4 addressing information was obtained automatically from a DHCP server, then the configuration on the DHCP server must be examined. So a configuration problem on a DHCP server usually affects multiple clients. Okay, it's not just your PC1 here. If your problem lies on the DHCP server. So how about troubleshooting IPv6 default gateway? So in IPv6, the default gateway can be configured manually using stateless auto configuration or SLAAC, or by using DHCP v6. So with SLAAC, the default gateway is advertised by the router to hosts using ICMP v6 router advertisements or RA. So the default gateway in the RA message is the link local IPv6 address of the router interface. So if the default gateway is configured manually on the host, which is very unlikely, the default gateway can be set to either the global IPv6 address or to the link local IPv6 address. Okay, so what you can do is you need to check R1 interface settings. Okay, so you could go ahead and type in show IPv6 interface, okay, and then the interface. So the command output on the show IPv6 interface G000 on R1 reveals that although the interface has an IPv6 address, it is not a member of the all IPv6 router multicast group FF02::2. Okay, so this means the router is not enabled as an all IPv6 router. So therefore, it is not sending out ICMP v6 RAs on this interface. Okay. Now you need to correct the IPv6 routing. Okay, so it's in here in figure 2. Okay, so R1 is enabled as an IPv6 router using the IPv6 unicast routing command here. So the show IPv6 interface G000 command verifies that R1 is a member of FF02::2. Okay, and that is an all IPv6 routers multicast group. Okay, so that's how we troubleshoot the default gateway if you are using the IPv6. Okay, so next is step 5. You have to verify the correct path. So when troubleshooting, it is often necessary to verify the path to the destination network. So the figure shows the reference topology indicating the intended path for the package from PC1 to SRV1. Okay, so the routers in the path make the routing decision based on information in the routing tables. So the IPv4 and IPv6 routing tables can be populated by the following methods. Okay, so you could have directly connected networks, local host or local routes, static routes, dynamic routes, and default routes. Okay. Now the process of forwarding IPv4 and IPv6 packets is based on the longest bit match or the longest prefix match. So the routing table process will attempt to forward the packet using an entry in the routing table with the greatest number of leftmost matching bits. So the number of matching bits is indicated by the prefix length of the route. So the figure here describes the process for both IPv4 and IPv6 routing tables. So examine the following scenarios based on the flowchart given. So if the destination packet or if the destination address in a packet does not match an entry in the routing table, then the default route is used. Okay. So if there is not a default route that is configured, the packet is discarded. Okay. So matches a single entry in the routing table, then the packet is forwarded through the interface that is defined in this route. So matches more than one entry in the routing table, and the routing entries have the same prefix length, then the packets for this destination can be distributed among the routes that are defined in the routing table. So matches more than one entry in the routing table, and the routing entries have different prefix length, then the packets for this destination are forwarded out of the interface that is associated with the route that has the longer match. Okay. Okay, step 6 is verify the transport layer. So if the network layer appears to be functioning as expected, but users are still unable to access resources, then the systems administrator or the network administrator must begin troubleshooting the upper layers. So two of the most common issues that affect the transport layer connectivity includes ACL configurations and NAT configurations. So a common tool for testing transport layer connectivity is Telnet. Okay, so you could use the Telnet utility. Okay, so caution, while Telnet can be used to test the transport layer, for security reasons, SSH should be used to remotely manage and configure devices. Okay, so the output verifies a successful transport layer connection, but R2 is refusing connection using port 80. Okay, so you'll have this closed by foreign hosts. Okay, next. So on routers, there may be ACLs that prohibit the passing or from passing through the interface in the inbound or outbound direction. Okay, So the use of the show IP access list command to display the contents of all the IPv4 ACLs, and the show IPv6 access list command to display all the contents of all the IPv6 ACLs configured in a router. So the specific ACL can be displayed by entering the ACL name or number as an option, okay, for this command. So the show IP interface or interfaces and the show IPv6 interfaces displays IPv4 and IPv6 interface information that indicates whether any IP ACLs are set on the interface. Okay, now referring to the first diagram here on the left side, okay, we can verify which interface has the ACL applied using the show IP interfaces serial 0/1/1. Okay, so and the show interfaces or show IP interfaces serial 0/0/0, okay, command. Now the output reveals that ACL was never applied to the inbound interface of serial 001, but it was accidentally applied to G00 interface, blocking all outbound traffic from 172.16.1.0/24 network. Okay, so based on our topology. Now, after correcting the issue, okay, so what happened here now is that after correctly placing the IPv4 ACL on the serial 001 inbound interface as shown in the command prompt, device can successfully connect now to the server. Okay? Next, step number 8. So next would be the DNS protocol controls the DNS, a distributed database with which you can map host names to IP addresses. So take note that DNS is used to resolve issues or to resolve IP addresses into names and vice versa. Okay, so when you configure DNS on the device, you can substitute the host name for IP address with all IP commands such as ping or telnet. Okay, so you could do something like ping IPv4 server. So instead of using the IP address. Okay, so this ensures that your IP address or this ensures that your DNS server is responding well. Okay, so to display the DNS configuration information on the switch or router, you use the show running command, okay, or the show run. When there is no DNS server installed, it is possible to enter names to IP mappings directly into a switch or router. Okay, use the IP host command to enter a name to be used instead of IPv4 address of the switch or router. Okay, so like what you have here. So after the successful verifications and your DNS is working fine, then you should be able to solve the problems on end-to-end connectivity. Okay, so in Windows platform, you can use the NSLOOKUP command to display the name to IP address mapping information. Thank you for watching and listening. Have a great day.